Okay, so welcome to Lecture 7. So we've done some forces. We're going to continue going in our journey here and start discussing some work and energy and how we're going to use forces to do that. So we're going to set up kind of a new environment here. I want to discuss what is known as a system. You can have a lot of different types of systems. It just depends on what is happening in the problem. Okay, so when I do say like a system here that a problem is in, it might be something of like what is taking place in it, right? So if we're talking about billiard balls on a pool table, okay, then that's the environment that we're talking about, is just what's happening on the table during that thing that's going on. It can be a single object, it could be a whole bunch of objects. It might even be like a region of space, right? So we might just say that in this space there's a pressure of whatever pascals or something, or a vacuum or something. And it can just be that region of space, maybe gas molecules inside of a pressurized jar. All right, then we're talking about that region of space within that jar. It can also vary with time and space. You might say that this system evolves as time goes on, and it might alter or change those objects that are in that system. The reason why we have to kind of introduce some new stuff is because Newton's laws are great and they work very, very well for simple systems. Okay. There are ways, Newton's laws are not incorrect, but there are problem sets that get very difficult if you're going to use Newton's laws. And we have different ways of just making them a little bit easier by using other variables. You would want to pick whatever equations would help you the most here. And to do that, we just need to learn a little bit more. So the first thing that we want to look at is work. Okay, work is what we're going to talk about in the physics perspective. So we're going to get to work by looking at work. Work. This is work done by constant forces. It's what you get when you apply a force to something and that object moves. All right, so if you push a box across the floor, you've done some work on that box, right? Or if you lift up a book off of a table, you've done work on that book. It's any time that you have to use a force to displace something. Okay, so there's some caveats about work here. It only counts if the force is applied in the direction of travel. Okay, that should be intuitively making sense. For instance, here we have this person pulling this box. You can see that there is a unit that has the force in the direction of the box's travel, right? And it would be the F cos theta. There is, of course, if we broke this vector down, there's, of course, a vertical component of that force, but that has nothing to do with the direction of travel. Those are 90 degrees apart. So we don't even worry about the vertical portion of that force because it doesn't apply to this. It only counts when the force is applied in the direction of travel. If you were to only push on the box straight up or straight down, you wouldn't get any travel, and that's why it doesn't matter. So we don't watch that. This is why we tag on this cosine function, okay, this cos theta, because of course when the cosine is 0, as in the direction of force, okay, and the direction of displacement, when the angle between those two vectors is 0, cosine of 0 is going to equal 1. And from all that, we get an equation here. Okay, work is then equal to force, magnitude of a force, times the magnitude of the change in r. Okay, it doesn't just have to be x, it could be y, it could be z, but some displacement, right? So force times the displacement, and then you have that cos theta. So the cos theta, the angle always depends on what is the angle between the two things that came before it. So in this case, our cos theta is what is the angle between the force, magnitude of the force, so magnitude of the force would be up here, and the delta R. Delta R in this case would be D. And the angle then between magnitude of the force, delta D, would be that angle there, whatever that is. So here's just a good picture representation of that. Hopefully that makes okay sense. And then you can see, of course, if you put in 90 degrees, if the force is 90 degrees with the direction of travel, the whole thing kills it. Cosine of 90 is 0. So the units of work, you can put them as Newton meters because it is a force times a distance. So Newton meters is fine. But it's more commonly called the joule, okay, or just a capital J. Joules, J. It's also not incorrect to have it be the full SI unit of kilogram meters squared over second squared, by the units of force and then the units of distance again. But it's so much easier and so much shorthand to just put joule. Okay, so that's the units of work. We call them joules. If there is positive work done, like for instance you push this box and it moves the direction that you're pushing, positive work means that you have added energy into the system. Okay, so you've put some energy in order to get that to move. If it's negative, if it's a cosine of like 180, then negative work has been done. Okay, so something has slipped away from you and it's caused work, or it's caused energy to leave the system. We'll talk a little bit more about that later on, but a positive work means added, negative work means the opposite, means energy has left the system. Okay, so this is actually the first time that we are seeing two vectors that are being multiplied by each other. Vector A times vector B. Before this, all we had was addition, right? We had scalars times vectors, but mainly it was addition is what we were looking at. So this is the first time we have some multiplication going on. When these things are paired up with a cosine function, just like what we have here, it's called a dot product. It's part of linear algebra, so it does fall under the algebra part of the course. And it's pretty simple to do. It's not it's nothing that's crazy difficult or anything. It just makes the multiplication easy. All you have to do here is just multiply up identical directional values, and we'll do some examples of these, of course. If the values are not in the same direction, like you have some in the x and some in the y, you don't multiply those together, because if there are opposite directions, like an x and a y or a y and a z, those things fall away to 0 because they're all 90 degrees apart. All right, so looking at this, again, I'll go over this more when we do the examples, but like directionals or identical directional values, like an I hat and an I hat, is going to result in a 1. Anything that is outside of identical, like an I hat and a J hat, those are going to go to 0. So any combination of these that are not identical goes to 0. So it makes the multiplications really easy. You just look for everything that's in the x, multiply those together. Everything in the y, multiply those together. Everything in the z, multiply those together. Okay, so we'll do some examples of that too. But I'm going to continue on here. We'll do those at the end. Of course, this chapter is riddled with calculus, but there's some ways of cheating calculus out of the equation. If that work that you're doing is being driven by a force that varies as with time as it goes through that motion, it would require calculus to determine what the total amount of work is. Lucky for us, though, there is a workaround. Here's our example where you have a force that is varying. It's going up and down as the distance increases, right? So you have this weird varying force. So being that work is force times area, or force times distance, you would need to kind of try and break this up into a bunch of little sections and do it individually, taking work to be a constant, roughly a constant at each of these little intervals. And then add all these up to get the total amount of work done. What that gets you is just the total amount of area that is underneath this curve. Okay, so you can see that here, if we did that, instead of having, I don't know, whatever, 15 or so columns here, if we did 1,000,000 columns, we would have something that looks more like this, and it fits very, very well underneath the curve. This area under here is force times the displacement. So this area would be the total amount of work that was done. So it's a workaround. Okay? So being that the total amount of work is equal to the total amount of area that's underneath the curve, if we give you very simple plots and graphs, we can just use algebra to solve for it. So it's a little bit of a workaround of cheating calculus. This is the actual calculus version of it. You take x, the change in x, to approach 0, so each of these gets smaller and smaller and smaller, and then you sum them all together and multiply those two things, the forces and the change in x. And of course what that looks like then is done an integral. Summing up something that is infinitely small comes up to be an integral, and in calculus we should be starting integrals now. But for calculus and for algebra it doesn't matter. The graphs that I will be giving you for the total amount of work done will be very easy, basic algebraic shapes that shouldn't matter. Okay, so in this case, if we're looking for the total amount of work that was done by this force, we would simply look at the area that's under the curve. So we can do this one together. I see here that force is at 5, so we have 5 newtons of force, and it looks like the first displacement goes 4 meters. So the area of the square would be 5 times 4, so we would get 20 joules of work for this square. And then we'd have to add this area of the triangle. So we have 20 here, and then we look at the triangle, and that has a height of 5 and a base here of 2, 4, 5, 6. So 5 and 2 would give me 10, and then it's half because it's a triangle. So basic area of triangle, 1/2 base times height. Base is 2, height is 5. So this would give us an extra 5 joules of work. So all in all, total, if I added up this area, would give me 25 joules of work that was done. Okay, so hopefully that makes sense. We'll do a few more examples of that as well. Moving on to the next portion here, we have a new force. We're going to also talk about springs. Springs work very well with work and energy, so we wanted to bring them in now. The chapter that was on forces already had a lot of forces, a lot of new material, so we don't want to include it in that chapter just because you're already learning so much and there's so much going on. So we look at it now. Okay, if we look at a spring, like we can see here in this this pictorial over here, you have the spring and it's being stretched. You have a block that's being stretched here, right? What does the spring want to do? Well, the spring wants to go back to its middle portion. We're going to call that x equals 0. It's the state of equilibrium. It wants to go back. If it goes back to the normal state, then it all seems fine, but usually there's some momentum and it goes past that middle point and starts to compress the spring. Now the force points in the opposite direction and it wants to go back out again. And in theory here, if the floor is completely frictionless, that spring will bob back and forth, back and forth, back and forth, endlessly. Okay? So what does that look like for work? Well, it means that every time we cross this line, the force flips direction and it wants to pull the other way. Right? So the force would be positive and negative and positive and negative. And the amount of force depends on how much you stretch the spring. Right? Stretch or compress the spring. So it ends up being a linear line, like this one here, where our force is a linear line that passes through the 0 point, because at the 0 point it is neither stretched nor stretched, so or compressed. So we end up passing through the 0 point with 0 force. But anywhere out of that, we end up with this force. Okay, if you pull it into the negative x, it will be a positive force. It wants to get away. If you pull the string past x, making x positive, the spring will want to return to 0, so it goes negative. All right, so these are how we get triangles anyway for the spring. You get these triangular shapes amount of work. There is a maximum, of course, to the springs. We're not going to delve into what happens when you overstretch a spring and it loses its state and that kind of stuff. We're just going to stay within the bounds of a normal spring. Okay. So the spring always wants to return back to that equilibrium state. This is one of the reasons here why it's one of the only forces that has a negative thrown in it into the equation. You can see the force of the spring equation down here on the bottom. It is F, and then I will give it a subtext S for spring. So force of spring is equal then to negative, because it always opposes it. And then there's a K, a lowercase k. That K stands for a K constant. It has all the information about the spring. It's spring specific. Right? Springs can vary quite a lot. You can have stiff springs that are like in a car or a bus, and you can have small mechanical springs in your lead pencils. So springs can change very, very much. The K constant, or the K factor, which is what this video and this whole page is about, is the different K factors in physics, just refers to the specs of the spring. This x here, even though it does not have a change in x, it is listed as x. That x is the displacement from the equilibrium point. Okay, you can see at the equilibrium point there is no force, so at that point x is equal to 0. K will never be 0 because it is a constant of the spring. So x can be a 0, and in that case we have 0 force. So this x term is simply how far away you have pulled or stretched or compressed the spring from its equilibrium. Okay, hopefully that makes okay sense on the spring. It's a new force we can add into our equation. Moving on, how do we get from work to energy? This chapter is supposed to be on energy. Well, work, it's really just a change in energy. Okay, you've put energy in moving that box. The energy is now in the box. So it's a change of energy. You doing work puts energy in or out of that system, or using a tool or a machine or an engine or whatever it is that you're creating this this force to move this object. Using work, we can do quite a bit of formulations to get some new equations. Okay, those will give us the equations of energy. If we know that work is simply a transfer of energy, we can then look at that change in energy and get an equation for energy itself. So for the algebra-based courses, really just worry about the final part of this this derivation, right? So your work here is just 1/2 mv squared, and it's going to be the final minus the initial, but the change in energy is known as 1/2 mv squared, okay, the mass times velocity squared. For all the calculus-based classes, it's good to really know the process of this integration, that you start with work, you put a generic force in, F is equal to ma, for instance, and then you want to integrate it with respect to displacement, to dx, between an initial and a final state. Well, we realize that a is just an acceleration. Acceleration we can write as a derivative, dv over dt. So we would have m dv dt times dx. And we can then do something a little bit strange here. We can add in an extra dx over dx, because that would just be a 1, right? Dx divided by dx. If we populate this in with another dx over dx, we could do some cross multiplication kind of stuff going on. So we would have dv dx dx dt times dx. I know it gets a little bit crazy in there, but it does work out just fine. Now we have a dx on bottom and a dx here, which are going to kind of cancel back out. So the dx's are going to cancel, and we're left with a dx dt. Well, what is dx dt? It's a velocity, right? So we've changed this this integration into now mv, so our mass times velocity with respect to velocity, dv. Okay. The reason we had to do that, of course, is because you're trying to take a derivative of something with respect to x, but there's no x. X is buried inside of acceleration, so you need to decompose acceleration in order to get that value of x. Anyway, this is what we end up with. An integration with respect to velocity with an equation that has velocity in it. This is an easy integration to do, especially if you're in beginner calculus or Calc 1. You just do the opposite of a derivative in this case, and we end up with 1/2 mv squared. Okay, so 1/2 mv squared is a form of energy. A change in that energy was equal to the work that has been done by an external force. So think of this. Your mass never changes. 1/2 m never changes. But velocity can change. We've got velocity initial and velocity final. What do you have to do to change your velocity? Right? To go from an initial velocity to a final velocity, especially if work is positive. Right? If you're going to speed up, if you're running, say you're running a marathon, and somebody passes you and you're feeling bad, and you want to get past that person, what do you have to do? You have to speed up, right? You have to put in more energy. You have to put in more work. That's why this takes place. Okay? A change in velocity means you're going to have to put in some energy. You're going to have to put in work in order to get where you want to go here. Okay, so that's our first one. That's all about velocity. The 1/2 m is a constant, but the velocity is changing. Okay, we call that kinetic energy. Now, I'm going to write it as K subscript E for kinetic energy. In your book or a lot of places online that you look are just going to have it written as a K. But it's equal to 1/2 mv squared. Okay, so it's just one portion of it. If you looked at the difference, it would be work. But if you're just looking at the energy itself, it's 1/2 mv squared. So there's going to be a collection of these equations for energy. You'll do it the exact same way. If you're in calculus, it's a great idea to go ahead and start plugging in these other forces. Right? So maybe instead of ma, the generic force, you want to plug in mg. Okay? If you run through that same equation with mg, you will end up with mgy. That's another form of energy. This one depends on gravity and the y displacement. So we call this the gravitational potential energy. So everything that's a potential energy, we give a character u to it. Not sure why, but we give it the potential character of a u. So I'm going to go with u subscript g for the gravitational potential, lowercase g. And this one depends on m, which stays the same, g, which is a constant, but y, okay, your height. So g depends on if you've changed something in height. And that should kind of come as intuitive as well. If you have to lift something up, you have to put some work into it. Y becomes more positive. You have to expel energy to lift things, right? If you let things fall on their own, energy leaves the system. Okay, if you just let something drop to the ground, it gains speed and it ends up dropping to the ground, and you've gained energy by not doing anything. You've released energy from the system. Okay? Another one that we could do, you do it the same way. You plug in a different force. We just learned a new one. That new force was the spring force. And we get something similar to the 1/2 mv squared. It's a little bit different. Again, algebra courses, you don't need to know the derivations. You just need to know the equations and how we got there. For calculus, I'd want you to work through the derivations, okay, just to make sure you've got them. But the potential spring energy, again, it's another potential, so we're going to call it a u, and we're going to go to subscript s for spring. And it's similar to the kinetic energy. It's 1/2 kx squared. Okay, it's how much energy is being stored in a spring. Okay. When you're doing problems that involve energy, it's really important that you ask the questions. What kind or kinds of energy are involved in this problem? Ask yourself if the problem contains each of the following. Okay. Is there a velocity change that is occurring in this problem? If so, you've got kinetic energy involved. Okay, because that depends on velocity. Is there any type of a height change? If there is, you've got gravitational energy. Or if there's something to do with a spring, that spring is changing its compression or stretch or anything like that. If there's anything with a spring, you have spring energy involved. So right now we just have the three. We will gain more as we continue to go through the semester, but these questions, will be asked in a lot of these different energy problems. It's kind of one of your first steps. Okay. Conservative versus non-conservative. So energy, you may have heard, can't be destroyed. It can either be transferred from one object to another, but it can never be destroyed. And where that is true, there's a couple of different ways of transferring energy. So when the energy in that system, say we've got a mass that's on a spring, when we can recover that energy, it's considered to be conservative. Okay, it's not lost to us. We can always recover it back. So if we think of this block in a spring, if this is a frictionless surface, it's just going to change place. So let's see, here we have kinetic energy because the mass here is not moving. We have compressed the spring to the x max. So the spring is not moving, so we have no velocity. But we do have a spring involved, and it's compressed, which means there's going to be some potential energy stored inside of that spring. So all of our energy right now is stored in that spring. Okay, hopefully that makes okay sense. What happens when we release the block? Well, x is going to get smaller, and as a result, velocity is going to increase. The mass is going to start moving, right? So this kinetic energy is going to start going up because all of a sudden velocity went from 0 to something higher. So kinetic energy will increase, and at the same time, our spring is losing x, which means the potential energy of the spring is going to go down. If we add both of these together, though, our total energy remains the same. It's still there. After the block has left the spring is now at 0, which means the spring does nothing anymore. The potential energy of the spring is 0, but now the block is moving with a high kinetic energy, V. And if this is frictionless, V will just continue on forever, which means our total energy is all kinetic, and it still matches total energy of the system. Okay, so this is a conservative problem right here. Okay, we've compressed a spring, we've let it go. All the energy has done is switched hands. Okay, but it's not lost. We've just switched it from gravity, or from spring into kinetic. If you want to think about it, if you put another spring on the other side, but you flipped it, right, what would happen there? Well, the block would go and it would compress the spring. All the velocity would switch back into potential, and then it would release the block again. It would go back into kinetic, and it would be this constant, endless go-between on the two springs of potential and kinetic. Okay, it would go back and forth. So for this reason here, kinetic and potential energies are considered conservative. Okay, lucky for us, those are the only ones we know right now. Kinetic and potential energies are conservative. Okay, if everything is frictionless, we can easily gain back the energy that we have. When the energy cannot be recovered, that's when it's a non-conservative force. So this includes all frictions and any kind of resistive force, air resistance. We had talked about terminal velocity. All of those forces that would make up work and energy are non-conservative because you can't get them back. Okay, for instance here, if this table has friction, and I have a book, and I move that book from point A to point B. Let's go along the blue path. All right, I'm going to give it energy by pushing the book. That energy is going to turn into kinetic energy because it is moving. Okay, but there's friction that's going to play part. Friction is going to push back on the book, and the velocity is going to continue it along. But we all know now, that when friction is involved, that book is eventually going to come to rest. We're going to lose all of our kinetic energy. And where is it going to go? So here, all of our kinetic energy is our total energy. As the book moves, that kinetic energy dwindles down to 0, and we have something called internal energy. Internal energy is usually heat transfer, friction in the book. You rub your hands together, you make heat. It's friction. But you can't get that back. You can't get that heat back to kinetic energy again. The book is never going to move again because you've heated it up. Okay, so that's a non-conservative force. You cannot get it back. Once the book stops, all the kinetic energy is gone. Everything is internal energy, and the total energy is now spent in internal energy. Okay, we can't get it back. This is an easy one to picture with friction. There's actually lots of other forces out there. There's a couple of properties to distinguish between the two. And those two are here. So if work is done by a conservative force on anything, on a particle, moving between any 2 points, it's independent of the path taken. So you can see here with our book, we're moving from A to B. A to B, if there's friction involved, A to B would be different than trying to take the red path. Right? So the red path would cause more distance to occur, you'd have more friction involved, it would take more energy to move it along the red path than the blue path. So if there's a difference between 2 points, dependent on the path, that is a non-conservative force. If it is independent of the path taken, it doesn't matter which path you take, it's considered a conservative force. Number 2 says if the work done by a conservative force on a particle moving through any closed path is 0, okay, so a closed path is one which the beginning point and the end point are identical, then it's a conservative force. So for instance, if you took a book and you raised the book up and then you brought it back to the exact same height that you had it at, you would begin at rest at a specific height. You'd raise the book. When you ended, you'd be back at rest, back at that same height, and you would have no change in any of those energies that we saw, right? Gravitational would be the same y, so that wouldn't cancel out. Final and initial would be the same. It would go to 0. Velocity, even though you moved the book, you brought it back to rest. No change in velocity between the start point and the end point. It's a closed path. And it doesn't matter if I just raise it up and raise it down. I can go left, I can go right, I can go in circles, loop-de-loops, whatever. It doesn't matter, because as long as it ends at the exact same point, whatever this path is, zeroes everything out if I bring it back to its identical initial states. Now see, you can't do that with this book, right? If I take the book, I let it go, it slides across the table to B. I need to put more energy into it to push it back over to A. So this does not work for the book example. That is why it is a non-conservative force. But gravitational force, absolutely conservative. Okay, because that one works very well. There's no friction there. We're moving things around. So it is problem specific, problem dependent. You got to look at it and see, is there friction involved? Is there something else going on here? Or can I use energy being conservative in the problem? Okay, well, that's the end of that one. Let's go ahead and get on to some problems. Okay, so here we are with our first example on chapter 7. We're going to start with the basics. So we started with work. So I've got the work equation up here. Work is equal to a force times a displacement times cos theta. Now these two are both magnitudes. Okay. If we want to look at it in the vector form, then we need the vector F dotted with the vector change in r, the displacement vector. So our first example here, we have someone trying to move a box. They're pulling on a rope. They're pulling this box with 50 newtons of force at 30 degrees. And what they're trying to do is move that box 3 meters. So the question says, calculate the work if the box is moved 3 meters. Okay, so for this one being, it's nice and simple. It's the first one that we have there. We know that we need a work equation. We have a work equation up here. We know that work is equal to the force times change in r times cos theta. Now, it wasn't given in vector form. It was given as magnitudes. 50 newtons was the magnitude. 3 meters was the magnitude. And it gave a angle for us. So I know normally what we do first off is break that angle down. And that's basically what we do by adding this cos theta in here, is we're breaking that angle down. So it takes a little bit of the guesswork out. To calculate the work, you just take magnitude of the force. So that would be the entire force. Okay, so the magnitude of the force would be 50. The change in R, the displacement, we want to move the box for 3 meters. Now, it doesn't matter if you're going left or right. You're moving the box 3 meters. And then the cosine of the angle. Now, this is the angle between R, the direction of motion, and F. Okay, so the force is traveling upward. The direction of motion is horizontal. What's the angle between those two? 30 degrees, given in the problem. Like I said, nice and easy one here. If we plug all that in, we should have 150 times the cosine of 30. I think it gives you just about 130. I think it's 129.9. And then the units for work are this new one, joules, or you can do it as a Newton meter. I prefer joules as kind of the more common one that you're going to see out there for a unit of energy. Work is going to be joules. Okay, we're all done. Let's box our answer. Nice and easy one for an example. We'll move on to the next one. Okay, so example 2 is going to be the second half here of the work equation, the dot product. So in this one here, if a box undergoes a displacement of change in R, so here we've got a vector quantity in its component form, 2i plus 3j, with a force of, and then another vector form, 5i plus 2j, what is the magnitude of the work done? Okay, so now being we have vector form, we need to use the vector form of the equation, or the dot product of the equation. Okay. So it's F dotted with change in R. So what I would start with here is getting the two vectors on top of each other. It just kind of sets this up a little bit better. It is F dotted with R, so I want to have F. I'm just going to rewrite it over here just for a little better clarity and in the proper order of F and then change in R. Okay. So for dot product, all you want to have is like-minded things, right? Getting multiplied together. You could also think of it as, like this if you wanted. You can also think of it like that, where it's the two vectors multiplied together. Anyway, writing them this way, writing it that way, keeping them in the equation, doesn't matter, as long as you know what you're doing and the steps you need to take. So remember, in a dot product, that I times I is going to give you 1, j times j is going to give you 1, k times k will give you 1, but any other combinations are going to result in a 0. So if I were to multiply these out, like you would normally do, like with sets in here, like you would multiply out, you would FOIL it out. You'd have 5i times 2i. So we would get 5 times 2 and then an I times an I. I times I is going to give us a 1. 5 times 2 is going to give us a 10. Now, if I keep going and I do 5i times 3j, that gives me 15. But the I and the j make it a 0. Okay, so it doesn't count. It's gonna fall away anyway. And now we'd have 2j times 2i. Again, we would get a 4, but it's times 0. Because it's j and I. It's two separate identities being multiplied together, results in a 0. And then finally, j times 2j times 3j is going to give me 6. And a j times a j gives me a 1. So what do we all end up with? We end up with 16. And of course, the units of work are joules. So that's why I prefer actually just writing them like this, because then you just multiply down. We have 10 plus 6, and we get 16 for our total number of joules. Notice there's no direction on it anymore, because I times I is equal to 1. It cancels out the direction. It's not a vector anymore. So this is just the magnitude of the work that has been done. Now, you might come across a problem that has you figure out the amount of work that's done, and then it might ask you for what is the angle between these two vectors. Well, you can use the relationship that this is both equal to work, and work is just a magnitude. So if you wanted, you could do the work, which is going to be 16, is equal to, we just did this to get the 16. Now we'd have to have the magnitude of f. And how do we find the magnitude of f when it's in a vector form? Okay. You use Pythagorean theorem, right? We're all the way back into vectors, chapter 3. You use Pythagorean theorem. And what would that be? So this is the work equals magnitude of f. Pythagorean theorem would say square root 5 squared plus 2 squared. That's the magnitude of f. And then this is multiplied by the change in r. Magnitude of the change in r would be square root 2 squared plus 3 squared. Okay, that would give you the magnitude of r. And then you have cos theta. And you just have to figure out what theta is at that point, right? So you have the 16. You have a number for f, you can just plug it in your calculator. You have a number for r, you can plug it into your calculator. Move these to the other side, divide them, and then figure out for theta. You have to use an inverse cosine. There's one of these in the homework. That's a pretty basic directions on how to do the one that's in the homework. So I'll let you finish it out there. But that's how you'd want to do it. Is since these are equalities and you already have the work, you already have the dot product done, go back and find the angle. All right, I'm going to move on to example 3. Let's check out example 3. Then we're going to have something a little different. We'll have a spring example. So I've added our spring equation for force. The spring force is equal to negative kx up in the corner there. And for this example here, we have a spring that is hung from the ceiling. It has a mass attached to it. That mass is 0.55 kilograms. And the spring here is being pulled downward or stretched by 2 centimeters. And what it's asking for is, what is the spring constant K? Okay, so using our new equation there, we see that the force on the spring is equal to negative kx. So that's where we're getting our K from, is the kx. X I have, it's 2 centimeters, although it's not written in SI units. So I can go ahead and change that over to 0.02 meters. And then I have this mass hanging out. So I don't have a force per se yet, right? So how am I going to find K constant? Well, I use the topics that we already know, right? I'm going to use power reasoning here, right? What's happening with that spring? Is that mass bouncing up and down, doing anything weird? It doesn't say so, so I'm assuming that it's just hanging there, being that the 2 centimeters is constant. So being it's a force, we go back and we go, hey, let's draw a free body diagram. What's happening on that mass? Well, we're going to have the force of gravity, which is mg, pulling that mass down, right? Now this one doesn't have a normal force. Instead, what does it have? It has a spring that's holding it up. And those two must balance in order for it to be in equilibrium, which means some of the forces in the y are 0. Okay? There's no forces going on in the x. There's no motion in the x. Nothing else is happening. So the x I don't need to worry about. So what are my forces in the y? Well, I have Fs pointing up. The spring force is holding it upright. And then, of course, Fg or mg is pointing down, right? So minus mg. So from this, I can see that Fs, my spring force, will be equal to mg. Okay, that gives me a solution there now to this problem. So if this is equal to mg, I can say now that mg is equal to negative kx. Now this isn't always the case. You got to watch it because this is only a spring that's hanging vertically with nothing moving. It's a simple problem, and things might get more difficult as you go. But we should have everything we need here. We should have everything we need now. So the M, 0.55. Okay. G is always just 9.8. Okay. G is always just 9.8. This is then equal to a negative K. This is the K that we're trying to find, right? That's the spring constant. And then what's the displacement of the X? Okay, so the X is being pulled down 2 centimeters, or this 0.02 meters. So I'm going to put it in as the negative 0.02 meters, okay, to keep everything in the correct SI units. All right, now what happens when I plug that into my calculator here? I didn't do this one out ahead of time, so let's do it together. 0.55 times 9.8. We're going to move that, we'll cancel out the negatives, and then we'll move the -2 to the other side. We'll divide it over, and we're going to get a K constant of 269.5. Okay. Now, what are the units of the K constant? Well, it's a force being divided over here by an X. So that would be newtons per meter. Okay. And there's our answer on that one. 269.5. Okay, basic one with a spring constant. Let's look at another one. Okay, let's look at example 4 here. So it's a somewhat similar problem that we had earlier. We have a box, and we're going to move that box 3 meters across the floor. This time we're going to give it 12 newtons of horizontal force. The box is a little bigger. We have a mass of 6 kilograms, and initially the box is at rest. Velocity is 0. So the question on this one is going to be, what is the velocity after the 3-meter push? Okay. So hopefully you can kind of see what's going on. We're pushing that box. We're going to assume that the ground is frictionless because there is no mu. It didn't tell us there was any friction. So always just assume, don't overthink it. Assume that the ground is frictionless unless it asks you for that. So how are we going to do this one? Well, the only equation I have with velocity so far up there is going to be the kinetic energy. Okay. I don't have a change in y, and I don't have a spring involved. So the only energy that I have is the kinetic energy, which I've added up there to the corner of the board. But all that does is it tells me kinetic energy is equal to 1/2 mv squared. I have the m, but I don't have v, and I don't have kinetic energy. So how do I got to figure that out? How am I going to do that? Well, I know that work is equal to the change in energy. All that is energy. It's just the change in energy. And being the only energy that I am working with, remember change is final minus initial. The only energy that I'm working with is kinetic energy. So I'm going to have 1/2 mv final squared minus 1/2 mv initial squared. Okay, but what is mv? What is v initial? Well, the box is at rest. So I know this is going to be a 0. This whole thing is going to 0 out. So that leaves me with work is equal to 1/2 mv final squared. Okay, seems like I'm still in the same boat. Now I just have a different premise, that work is equal to mv final squared. So how do I figure out work? Well, work, I have an equation for that, is equal to F change in R cos theta. What is F? We're giving 12 newtons of force, which means I'll have 12 newtons. The change in R means I'm going to have 3 meters. And then what is the cosine of the angle? Remember, the angle is dependent on these two things. It's the angle between the force and the direction of travel. So here I have force traveling to the right. I also have the box traveling to the right, which means this is going to be the cosine of 0, or just 1. So I'm going to get 36 joules for the work. If 36 joules is for the work, it means I can put in 36 here for work. All right, now I'll have 36 is equal to 1/2. My mass is 6 kilograms, V final squared. Half of 6 just so happens to bring me to a 3 again. They're not connected, but it just happens to bring me back to a 3. If I divide 36 back by 3, I'll get a 12. And that's VF final squared, which means what? VF is then equal to the square root of 12. What's the square root of 12? I believe it's around 3.5. So what's the velocity here? It's about 3.5 meters per second. 3.5 meters per second. Does that seem about right? 3.5 isn't that fast. It's a small block, 6 kilograms and 12 newtons on it. Sure. It's not anything crazy. We're not at speed of light or anything like that. Sure. 3.5 meters per second sounds good. And you might get some questions that are multi-part that are also asking, well, how about the work done by other forces, right? So in this one, we did it by the acting force, the 12 newtons. That's why I put F in here as 12. Why didn't I put gravitational force, or why didn't I put any of the other ones in there? Well, you can do those. If we did work done by the gravitational force, for instance, we'd have Fg change in r cos theta. Now, this isn't part of the problem, but this is just an example of it. How much work would be done by the gravitational force? Well, I know that that's just m times g. And then I'd have the change in r. But what's my cosine? What's my angle between this and this? All right, so the Fg is always going to point down, right? If we do a free body diagram, Fg points down. This is our acting force, and that's our normal force. Fg points down. The direction is to the right. What angle does that make between the two? It makes 90 degrees. 90 degrees between those. Okay. Or you could put it in as 270 if you want. It doesn't matter. 90 degrees between it. What does the cosine of 90 give you? It gives you a 0. Okay, so no work is done by the gravitational force because there is no direction of travel in the y direction. That's not always the case, but it is in this one because the direction of travel is only along the x-axis. Sometimes gravity will do work if a box is sliding down a hill, or if we are having to push a box up a hill, and we are going in that same, a portion of our direction is in the same direction as gravity or against gravity, then we'll have some work by the gravitational force. But in this case, we don't. And it works the same with the normal force. If I was to put the normal force in here, normal force and the change in r, those are also at 90 degrees, so I'd have a cosine of 90, I end up back at 0 again. All right, so you'll see that on some multi-part stuff. Quick and easy points. If you understand what's going on, you don't need to show much work. You just go, boom, it's 0 because they're 90 degrees apart. Okay. Hopefully that made sense. Let's jump into it. So example 5, I'll give you one that's a little bit tougher, and then we'll move on to the next chapter, which also deals with energy and work. So you'll get more examples in that one as well. But for example 5 here, let's say that you're out riding your bike and the chain falls off, or you've got flat tires or something. Anyway, your bike's broken, and you have to push it now up this hill to get it home. How much work will be done? How much work will it be to push your bike up this 30-degree hill? A bike weighs 30 kilograms. Sorry, bike weighs 20 kilograms. It's a 20-meter long hill at a 30-degree incline. So we want to know how much work needs to be done. Well, we know that work is just a change in energy. It doesn't give us any type of a force on this one that we're putting on the bike. It doesn't give us, that. So we can default to work is equal to change in energy because we don't have that. Okay. What type of energy are we using? Well, in here, it doesn't specifically state it, but let's say it's at constant velocity. Now it states it. So let's assume that it's at a constant velocity, which means that the kinetic energy will be zero. There's no change in the kinetic energy. If the V remains the same all the time, final and initial will be the same number, and there's no change in kinetic energy. How about gravitational potential? Yes, there's going to be change in gravitational potential. We'll have an mgy. We have two different y's. You started here and you ended here. Okay, is there a spring involved? No. So we have no spring involved in this equation. We have no spring involved for our energy on there. So our change in energy is strictly going to be the mgy. So we have a y final, mgy initial. Okay. Now the initial, it didn't state how low we are here, but the initial is on the ground at the bottom of the hill. So we can assume that to be the zero position, right? So we're going to assume that this is the zero position of y, which means that part goes away. So if this is considered zero, what is this considered for the y? Well, for that, we have to do a little bit of trig. Back to chapter 3, vectors and trig, and find out what the height of the hill is. Okay. So we have the adjacent. We're looking for the opposite, because opposite of that angle would be the height, and it's a 30 degrees. So what does that mean? It means we're going to have a tangent. Okay? It means we'll have a tangent. So we'll have tan of 30. Remember, tan of 30 at SOHCAHTOA, so OA, opposite over the 20. Okay, so what does that mean? It means I just need to take 20 times the tangent of 30 degrees, and that'll give me an 11.55. Okay, so the height on this thing is 11.55 meters. Okay, and that's by putting the 20 to the other side, taking the opposite. Opposite is then equal to 11.55 meters. Okay. Anyway, so now I have the height change, right? Which means my final is going to be 11.55 meters higher than my initial. The mass is 20. G is always 9.8. And now my Y final will be 11.55. Grab a calculator, throw that in there, and what do we get? We get 20 times 9.8 times 11.55. We get the total amount of work needed to push that bike up, 22, or in around 64 joules. Okay. That's the amount of work that was needed to push that bike up the hill. Okay, so hopefully that should make some okay sense. Let's say this was just a part A. So we'll make this one a little bit tougher. And we'll say B, with what initial velocity would you be able to ride the bike? We'll say coast. Because remember, the bike's broken. Coast your way to the top of the hill. Okay, so with what initial velocity would you be able to coast the bike? So you're going to run, right? You're going to take your bike and you're going to run, get a good fast speed, hop on the bike, and hopefully you've got enough speed that it will carry you up this hill. Okay. Okay, so hopefully you get that for part B. That's what we're asking. Let's look at part B then and say, well, if this is the amount of work that was needed in order to get the bike up the hill, then this is the amount of work that is needed if instead of potential energy, I'm looking at kinetic energy. Okay, so kinetic energy would be 1/2 mv squared. And of course, it's final minus initial. And that would be the change in energy. Okay. So for this one, let's see, if we look at the equation here, 1/2 mv final squared. What do I want my final velocity to be when I reach the top of the hill? Well, it can be anything I want, but there is a minimum, right? I need it to at least be positive or 0 when it reaches the top of the hill, right? I don't want to get partway up and not make it. The absolute minimum would be I get to the top of the hill and the bike just comes to a stop at the very top of the hill. So my final can actually go to 0. And that leaves me with a negative 1/2 mv initial squared. Okay, so that doesn't tell me how fast I need to go, but it tells me the amount of work that would need to be done in order to get up there. Now, this is the work that we have to do, 2264. This would be the amount of work we have to put in order to get the bike up the hill. In this case, we're fighting that work. That work is done by gravity. We are fighting that work. So what we need here is to put in a negative 2264. Okay. Negative 2264 is then equal to the negative 1/2 mv initial squared. And that might make more sense in the next chapter as well, while we put in the negative there. But it's because we're not grabbing this work as is. This is the amount of work we would have to put in. So this is the amount of work that would need to be drawn out of the system, right? Negative need to be drawn out. So this is the work that is needed off of gravity. Anyway, moving on. The two negatives are going to cancel, okay? And then we'll multiply by 2, and then we will, well, let's see, I'll do some of it out here. So we'll have 2264. I'm going to multiply it by 2 so that I can get rid of this half. Okay, so that's going to make 4528. And what's my m? My m is now 20. Okay. Vi squared. Divide that by 20. And we'll get 226.4. That's Vi squared. To get rid of the square, we need to square root both sides. And if we do that, we see that we need an initial velocity of Vi of 15. Better go 15.1. We'll round up because we got to have a little bit extra in there just to make it to the top of the hill. We're around 15.1 meters per second is what we're going to have to get that bike up the hill. Okay. Now this is, I guess I stated it wrong when I said you would jump on the bike and ride it to the top. This would literally be throwing your bike because the 20 kilograms is the bike only. So if you could push the bike fast enough and have the bike coast up to the top of the hill, that's what this problem is about. 15.1 meters per second, is that doable? Yeah, probably. It's probably all right. It's not that big of a hill. I think the bigger trouble would be getting the bike to stay upright as you throw it up the hill. But anyway, it's just a dumb example. Just a quick little example of how we can go from one to the other as well. Okay.